Okay, this is a extra credit lesson, chapter 2, section 8 on similar figures. You should only be doing this lesson if you have 100% on that sheet of paper that I gave you on everything. If not, you need to go to those lessons that you have not done yet before you do this, because otherwise it's really not extra credit, because it doesn't really give you that extra, or it doesn't really give you the reward that you get at the end. Now, it does go in as 100% if you do it, but it's not the true extra credit that you want at the end if you don't have it done. This lesson on similar figures is typically covered in geometry, but since we just learned how to do proportions, it's a good time to introduce you to it. It's not really going to be on a test, but if you are ahead of the game right now, as you are supposed to be, then you may as well try it out. Whenever two items are the same exact shape but different sizes, we call them similar figures. If you're looking at a map of the United States, the image of it on the map is supposed to match the shape of the United States. Those are two similar figures. Whenever you're talking about a model car or a figurine of, let's say, the Eiffel Tower is created to match the shape, those are similar figures. Even a picture, if you take a picture of something, the image of that picture is a similar figure of whatever it is, and it's usually much smaller, but sometimes much larger. For example, if you take a picture of a hotel, the hotel is a lot bigger than the picture, but the picture scales it down to where you can actually see some things, measure some things, and all that. Or if you're talking about something like a bug, like an ant, or a spider taken in a picture and blown up, it's going to be much larger than the actual size. Because we know how to use proportions, we can use similar figures to draw conclusions about some things. So let's just look at some situations and see how it applies. Because like I said, it's not that hard. It's just a matter of making sure you understand how it works. These two triangles are similar. Anytime they are similar, again, it means they have the same exact shape. It's just that one is a little bit smaller than the other one. And so what we can use is the fact that these two things are related to create a ratio or proportion. And what you can do is say, take the sides that are in the same exact location and simply put those two into a ratio. So 7.5 is the big triangle, put it over 5, which represents the same side in the small triangle. And then what you will do is, and I'm using two different shapes on purpose, again, this is the bigger triangle to the smaller triangle. The bigger triangle here is 18. The smaller triangle here is x. And so again, 7.5 over 5 should be the same as 18 over x. This bigger triangle side to the smaller triangle side should match the bigger triangle side to the smaller triangle side. And so from there we do our proportion work. 5 times 8 is 40, so it would be 90. Then you divide by 7.5. And 90 divided by 7.5, I do not know, which is 12. Let me make sure that it actually is 90 before I mess this up. Yep. So what that tells us is that if this is 7.5 and that's 5, then that would be 18, this would be 12. Now that is the geometry, over the main geometry use of it that you'll see, but the actual application is useful in terms of situations like this. Let's imagine that you are somewhere at a park, or you're building something for a park, and there's a lake there that you obviously cannot measure the distance across the lake. But let's say you have to build a bridge, and I don't know what this question is talking about yet, but this is a true application of how proportions can be used. What you can measure, though, is the distance from a point way out here to this side, and a distance from this point on a straight line up to here. You can also measure a side that is you can actually walk across and measure here. And what you can use then is the fact that these two triangles are similar to say, if I know this size, then I can pretty much figure out what this size is. So what we're going to do here is look at that. It says in the diagram of the park, it says triangle ADF, which is that triangle, is similar to, that's what that little symbol means, kind of like a squiggly N, is similar to triangle BCF. That means, again, they are the same shape. The crosswalk at point A is 20 yards long, so this is 20. And then it says a bridge across the pond will be built from point B to point C. What will the length of the bridge be? The best thing to do in this picture here is to draw both triangles again. So what I would do is I would take the smaller triangle and pull the information. I know it says that the distance here is 20, so put a 20 right here, and this figure shows that this distance is 50. In the bigger triangle, I don't know what this is, so we'll put an X, but I know that this distance based off of the figure is 120. And once you've taken that image or that information out, now we have the same thing as we had up there, which, as I said, didn't have any real use, but this one does. And so what we can do now is say that 50 goes over 120, and therefore 20 would go over X. And now we solve this and we find out how big that bridge would be, and you get 50x equals, I think that's 24 with 2 zeros. Now what you do is divide both sides by 50, and I think you get 480. I think, let's see, 2400 divided by 50, oh, 48, sorry. So 48 would be your answer on that, and that is it. Alright, so what that means is, you know that this distance here is 50 because you can measure it. You know this distance here is 120 because you can measure it. You know this distance here is 20, and then you can tell somebody that you need them to have a 48-foot bridge to get built from here to here, because you actually know that it's 48 feet from this distance to that distance. And again, that would be the actual application of it, or one actual application of it. There are other situations like number 17 on the notes, at least these are from the book, where it talks about a model maker building a giant scale of a fly to be used in the science fiction film. So, you know, like the things, maybe even if you're doing a float at a parade, where you take something and blow it up and make it bigger, or bring it down and make it smaller. It says the actual fly is 0.2 inches long, and it talks about the wingspan being 0.5 inches, and then it says the model fly is going to be 27 feet long. So what we are doing here is we are taking a 2-inch fly and turning it into a 27-foot fly. And so what we want to do here is take the numbers that are related, which is that the actual fly is 0.2 inches and he's going to be 27 inches, and then create our model. And again, this is the actual fly and the model fly, because this is 0.2, which is the actual fly, 27 feet, which is the model. We talk about the wingspan being 0.5, and all you have to do is ask yourself, is this the actual fly's wingspan? And of course it is, so that means that 0.5 stays with the real fly. This is the model. And so 0.5 goes here because we want to know what the wingspan of the model is going to be. Again, the real fly compared to the model fly equals real fly compared to model fly. And from there we solve it. So 0.2x is 27.5, which is 13.5. Divide both sides by 0.2. And you get 67.5 feet. So you'd have a 27-foot fly with a 67-foot wingspan, which is actually pretty big. But again, that's how you can use it in that situation there. Again, most of what it is in the scale situation and the model situation. It talks about a particular model rocket uses a scale 1 to 44. The actual rocket is 168 feet tall. The easiest way to do it, and let's say that this is 1 inch equals 144 feet. So what you can do here is you can put your 1 over your 144, because that is your scale. And then you can kind of use what we did on the airplane problem and say if 168 is in feet and 144 is in feet, that you can put the 168 with the 144, because of course the 168 is what the 144 represents. We want to know how tall it will be in the model. So if the model is 1 inch compared to 144 feet, then we want our rocket to be turned into a model. And so you get 168 equals 144x. To get rid of that, we divide by 144. 168 divided by 144 is 1.17. And so the model is going to be 1.17 inches tall, or if it was feet, then it'd be 1.17 feet tall. So that is what you're doing. So what you want to do now, again, this is if you are finished with everything, is to go ahead and log into MathXL and complete the assignment titled Chapter 2.8 Extra Credit. If you earn 100% on this, then that allows you to skip one assignment this quarter, this whole quarter. This only works if you've already earned 100% on everything else. So if you get 100% today and you have not gotten 100% on everything else, then you cannot skip an assignment this quarter. If you get 100% on this and then you go back and finish everything else before you leave today, then you can skip something. But if you leave and you still have a 0 anywhere, then this is just an extra 100% that I'll put in the book, but it does not allow you to skip one assignment. So hopefully you did this the way you were supposed to, and we'll see what's happening. Good luck.